All right, guys, welcome back to class. So, this is Unit 5, Lesson 12, 3 Ways to Represent Motion at a Constant Speed. This is a lesson that I did with our morning group. This was right at the end of one of our last days of class. I think it was on Friday. And we had a ton of kids missing in our afternoon group. So morning group has already had this lesson. I think it'll be good review for them, and it'll be a new lesson for afternoon group. The whole objective of this lesson, we're going to be making a table and a graph based on an equation. And we're also going to relate the equations and the graphs and the tables for constant change situations. So we're going to kind of treat it like class, where I'm going to be kind of doing things on the video here, except it'll be here instead of on a screen. And I know you guys don't have your books to follow along, which is kind of a bummer. So if you want to try to log into Think Central, you can print off the pages if you want, but I think my best suggestion is to kind of follow along during the video and then kind of try to do the homework page on your own like we typically do. So let's go ahead and get started here. So we're going to suppose a high-speed train travels at a constant rate between Greenville and Orange Lake. T is going to represent our number of minutes elapsed, and D is going to represent the number of miles the train has traveled. So some more information that we have is that D and T vary together, which means as one gets bigger, so does the other one, which should make sense because if it's a train moving, the longer the train goes, the more time or the more distance the train has traveled. So in this situation, the relationship is represented by the equation D equals 2.5 T. So T is going to be the independent variable, which means that time is going on no matter what, and D is the dependent variable. So how many miles have traveled depends on how much time has passed. So we're going to go ahead and complete this first table here, and we know that if 0 minutes have passed, how much miles have been traveled? Well, 0. And if there's 1 minute that has passed by, how many miles have been traveled? Well, if you're not sure, you can plug in your numbers into the equation here. So if D equals 2.5 T, and we're saying that T is 1, we're going to change this T to a 1, and we're going to multiply 2.5 times 1, because we know in algebra that if you have a coefficient right next to a variable, we're just going to multiply them. And so 2.5 times 1 will give us our D, which is our distance. So in this case, 2.5 times 1 is 2.5. So D equals 2.5. Now for 2, let's change colors here. If we want to figure out how many miles were traveled in 2 minutes, we can use that same equation, D equals 2.5 T. Again, we're getting that from right up here. And if we want to know how much distance happened in that many minutes, then we can say, well, if our time is 2 minutes, according to our table, we can say our T is 2, multiply that by 2.5, and we can get our distance. So 2.5 times 2, we should be able to do that in our head. Doubling 2.5, we get 5. So 5 miles have been traveled in 2 minutes. So I think I'm starting to see a pattern here. We go from a 0 to 2.5. We are adding 2.5. Now from 2.5 to 5, we are adding 2.5. I'm going to go ahead and make a prediction here that my next answer is going to be adding another 2.5. So I think if I add 2.5 to 5, I'm going to get 7.5. But let's go ahead and check with our equation just to make sure. So we'll do a third color here. D equals 2.5 times T. So D equals 2.5 times, we're trying to multiply it by 3. Now 2.5 times 3, if that's not one you can do in your head, it's always okay to do some math off to the side. 2.5 times 3. 3 times 5 is 15. 3 times 2 is 6, and 1 more is 7. We're going to move our decimal place 1 movement, and we get 7.5. Hey, that's what we said. All right, so I think I can go ahead and finish the table here because we are just adding 2.5 every time. So 7.5 plus another 2.5 is going to be 10. If we continue that pattern of adding 2.5, it's going to be 12.5, and we'll finish it off with 15. So finish number 1, we made the table. Now we're going to go ahead to number 2. We're going to graph those points from the table. So on our graph, we are treating our t as our x axis, which we can see right here is the x. They have that labeled as the t. And our y-axis is our d, or our distance, which is going to be up here. So again, this is like our x-axis, and this is our y-axis. So these turn into coordinates. So we have our first pair is 0, 0. We can go ahead and graph that coordinate. Then we have 1, 2.5. So remember, on a coordinate grid, we're going to go over 1 and up 2.5. So over 1 and then up 2.5 is going to be right here. Over 2, up 5. Over 3, up 7.5. Over 4, up 10. Over 5, up 12.5. Over 6, up 15. All right, now, does it make sense to connect the points on this graph? Sometimes it does, sometimes it doesn't. So when we're talking about in between points on a graph, just like we've discussed in class in the past, we've said, well, are there points occurring in between the points that we actually graphed? In this case, yes. If you travel for, let's say, 2.5 minutes, is there a possibility that there's a point here that we didn't label? Well, of course. If you travel 2.5 minutes, you're going in between those 2 points right there for how far you traveled. You're going in between 2.5 and 5 miles, somewhere in there. Or sorry, not 2.5 and 5 miles, in between 5 and 7.5 miles. So yes, we can go ahead and connect our dots because there is distance traveled in between the minutes that are passing by. So yes, it does make sense. Then we're going to draw a unit rate triangle on your graph. Remember, a unit rate just means how much is going in 1 unit. So here's our 1, there's a unit. And if you wanted to make your unit rate triangles continue, you could. It looks a little bit different on this graph because we are kind of in between numbers on our y-axis here. So if you wanted to keep going, this one actually would look a little different than what we're used to because some of our coordinates are happening in between numbers on the y-axis. So it's not following the grid that's already there. But your unit rate triangle should be the same every single time. It should be the same size. That's the whole point, is in 1 unit, how much is changing. Okay, number 5, what is the speed of the train in miles per minute? In other words, what is the unit rate? So for 1 minute, how many miles have been traveled? So just like we've done since the beginning of the year, a unit rate that comes from the prefix uni, which just means 1. So we can go back to our table here. We can say, well, in 1 minute, how many miles? 2.5. So 2.5 miles per minute is our unit rate. Okay. So number 6 is a class discussion. Unfortunately, we're not doing a live video, so this is not going to be a class discussion, but it says, how are T and D related on this equation, in the table, and on the graph? So we can't really discuss this as a group, but we can see that D and T are both moving up at the same time. So as T increases, so does the D. And we do know that for every 1 minute of time, we are growing 2.5 miles in our distance. So I would say that our distance is growing more quickly than our time, but they are both going in a positive direction. All right. Let's get flipped over to our next page here. All right. So now we're looking at kind of a silly little story here. This is called Superhero Supplies. So in this situation, there are different superpower soups. In the factory, each type of soup flows into a different vat, and a vat is just a big pot. So you can imagine they have these soups that are coming out of a machine. I don't know if I could draw a little faucet here with like a little thing at the top. I don't know, kind of like a sink, right? You turn this and then it starts coming out, okay? And so these situations are going to be telling you the longer that the what is it called? Just the faucet, I guess. The longer that the soup is coming out the faucet, how quickly is the vat filling up? This right here is the vat. Again, a vat is kind of just another word for a bowl. So we're going to be looking at different situations of different soups, and it's kind of an imaginary story. Each soup has a big superpower. So just like we've done in the past, T represents time. In this case, we're being more specific in saying the time is seconds, how much seconds have gone by. And V doesn't mean vat in this case. V stands for volume, which is a measurement of liquid. So it's how many liters of soup are going into the vat, okay? So again, this is time, and this is volume. Not volume on your radio, how loud something is. Volume is how much space the liquid is taking up. So how many liters of soup? All right, so for each vat, V and T vary together, which again just means that they're both increasing, and they are related by an equation. So there's different vats. We have vat number 1, and this is the soup for super strength. So in this imaginary story, if you drink this soup or eat this soup, you're going to have super strength. And this is how it fills up. The equation of super strength is V equals T squared. Okay, so the volume of the soup filling up that vat is equal to when you square the time, or V to the second power. So we're going to complete the table. And when you are completing a table in math, what you need to do is, this says for vat 1, it's telling you the equation right here is V equals T squared. You need to start plugging in some numbers for your equation. So we're going to do this multiple times. V equals T squared. So on this side of our chart or our table is the T. So if T equals 0, we're going to put a 0 in for T. And that'll give us our answer on the right side of our table for what is the V, or the volume. So when T is 0, what is V? Well, what's 0 squared? 0 times 0 is just 0. So we end up with V equals 0. Okay? We're going to try to figure out for 1. What if V equals T squared? Instead of 0, now we're going to say 1. So V equals 1 squared. In other words, V equals 1 times 1, which is 1. All right, so we can do it again. V equals T squared. V equals, this time, if 2 seconds go by, 2 squared, 2 times 2, and we get 4. Okay, I think we can do one more, and then we'll start kind of seeing the pattern that's going on here. So V equals T squared. This time, T is going to be equal to 3. And that's 3 times 3, which is 9. So I'm noticing a pattern here in my chart where I'm not going to have to continue doing every calculation. I can see that you're just squaring each number. So this is 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. So if I continue that pattern, 4 times 4 is going to be 16. 5 times 5 is 25. 6 times 6 is 36. So our table is complete, and now we get to make a graph of what this table looks like. So at the beginning of this lesson, we said that the whole objective of the learning here is to relate an equation to a table and also to a graph. So we turned our equation into a table, and now we're going to take the information on that table and see what it looks like visually on a graph. So we're going to plot these points. Remember that the first one on the left, our time, is like our x-axis. The one on the right, our volume, our V, is like our y-axis. So we're going to start plotting these. We have a 0, 0, 1, 1, 2, 4, 3, 9, 4, 16, 525, and a 636. All the way at the top there. Now, is the soup, oh no, number 8, connect the points if it makes sense to. So we plotted it. Now, does it make sense to connect these? Remember, when you're asking yourself, does it make sense to connect them? You're asking, is there information happening in between these points here? So if 1 second has gone by, 1 liter of soup has filled up. Well, what if it was something in between that? Like, what if half a second went by? Does that mean some soup came out in that half second? Of course it does. The soup is flowing in between the seconds, not just every second it squirts out. It's squirting out the whole time. So yes, in this case, it does make sense. So we're going to do our best to connect these. And we're seeing a picture of what this equation looks like. So this equation has these numbers on a table, and it looks like this when you draw a picture of it in a graph. Is the soup flowing into vat 1 at a constant rate? And you can ask yourself, well, can I make a unit rate triangle that is the same every time? And in this case, the answer would be no, it is not the same every time. I'm going to flip back to our previous example. This one did have a constant rate because every single unit rate triangle was the same size. On this one, if I have 1 unit, first it goes to 1. If I do another one, it jumps all the way up to 4, and then to 9, and then to 16. This is not a constant rate. These are not the same at all. Okay, so let's try a different one. We're going to complete the tables for vats 2 and 3. So this time we have 2 different equations on here. We have more superhero soup. Let's see, the one we just did was for super strength. So vat 2 is for x-ray vision. So this is our x-ray soup. And then vat 3 is for flying. That sounds fun. I wish that was really a soup. If I could have a soup that made me fly, I would totally eat that for lunch every day. It'd be awesome. All right, so we get to fill out these charts. Now again, how are you filling out a table? You are just plugging in the letter T, all the numbers for the letter T, you plug it into your equation and see what your V comes out to when you do the math. So on this one, I'm going to do V equals 5T. And I can simply just put my numbers in for T. So I'm going to start out with 0. So if T is 0, 5 times 0. V is going to be equal to 0. Well, what about if my time is 1? So V equals 5T. V equals 5 times, instead of 0, this time my T is 1. Well, it equals 5. Okay, what about my next one? What if my T is 2? So V equals 5T. Again, every single time, I'm just starting with my equation and plugging in the letter T. I'm plugging in the number that it gives me. So I have V equals 5T. So V equals 5 times, this time, the T will be 2. And we get 10. All right, well, I'm starting to see a pattern here that every time I'm just multiplying it by 5, which is what my equation said in the first place. So I don't think I need to do any more equation work. I can just fill this out. 0 times 5 was 0. 1 times 5 was 5. 2 times 5 is 10. I think I get the pattern. 3 times 5 is 15. 4 times 5 is 20. 5 times 5 is 25. And 6 times 5 is 30. So if I went ahead and did my next one, I could see that it's going to be a little bit different. This time it's V equals 5T plus 3. So I'm going to have a little bit of extra work to do on here. So it's the same idea where instead of a T, I'm putting in my number, which in this case is 0, and then I'm going to add 3. So if I follow my order of operations, my PEMDAS, I have to do my multiplication first. So 5 times 0 is 0, and then I get to add 3 more. So in this first case, V is actually equal to 3. Well, let's try my next one. V equals 5T plus 3. That's just my equation that I started out with right here. okay? And if I plug in 1 for my number t, or for my letter t, I have 5 times 1 plus 3. Order of operations says I have to do my 5 first, then I can add a 3 to it, and we get 8. All right, let's do another one. So v equals 5t plus 3. So 5 times t is 5 times 2, because we're on my number 2 right here, and then we're going to add 3 to it. Order of operations says multiply first. 5 times 2 is 10, and I add 3 to it to get 13. All right, do I have enough to figure out a pattern here? 3 started at 3. This looks like maybe a plus 5 to get to my 8. 8 is going to be plus 5 to get to my 13. Well, I'm thinking I can probably do a plus 5 here for my next one, and I can end up at 18, but I want to check just to make sure. So v equals 5t plus 3. We'll do it again. This time my t is 3, so 5 times 3 plus 3. Order of operations, do my multiplication first. I get 5 times 3 is 15, plus 3 more. Hey, I do get 18. That's what I wanted to see. So I can tell for sure my pattern, it started at 3, but every single v after that is just adding 5. So 18 plus 5, 23. Plus 5 more again, we get 28. Plus 5 more again, and we get 33. All right, so we figured out our tables, and now we're going to plot these. So first it says plot the points for VAT 2. That's going to be our x-ray soup. And we're going to connect our points if it makes sense to. Yes, it does make sense because we are trying to figure out how much soup is flowing into it. And the soup flow is always going. It's not just shooting out every second. It's shooting out in between all the seconds too. So we're going to first plot VAT 2, and I'm going to do green because my table wasn't green. So we're going to start out with 0, 0. Go over 1 up 5, over 2 up 10, over 3 up 15, over 4 up 20, over 5 up 25, and over 6 up 30. And yes, we are going to connect them. It's best to use a straight edge, but I'm just gonna wing it. All right, now use a different color to plot the points for VAT 3 on the same grid. So we're gonna actually plot both of these at the same time. So I'm gonna use orange for VAT 3, which is my flying soup, because I used orange when I filled out that chart. So this has the coordinates 0 up 3, over 0 up 3, 1, 8, so over 1 up 8, 2, 13, 3, 18, 4, 23, 5, 28, and 6, 33. And again, I am going to connect these for the same reason as before. And then it asks us a question. Number 13 says, tell whether the soup is flowing into the vat at a constant rate. So for VAT 2, that's green. Is that at a constant rate? If it is, then the unit rate triangle will be the same for every single step. And as you guys can see, those unit rate triangles are all identical. They all have an over 1 up 5 change in the triangle. So yes, the unit rate is the same for all of them. Now, what about VAT 3? Making the unit rate triangle looks a little different here because it started up higher on the graph, but it is also the same. And I know this starts to look a little bit messy on here, but if you can concentrate on just that orange, it says over 1 up 5, over 1 up 5. Every single unit rate triangle is over 1 up 5. So yes, it is also the same. So now we get to interpret the equation a little bit. So in V equals 5t, what does the 5 tell us? What does the 5 tell us there? Well, it's telling you the rate of flow for the soup in liters per second. So for that soup, it's coming out in 5 liters every second, okay? Well, the next equation was a little bit different. This one was V equals 5t plus 3. So what did the 3 tell us here? Well, it almost looks like the same equation. They both have a V equals 5t, but this time there's an additional 3 on the end. So what is that 3 talking about? Well, the 5t is the same. It's still the rate of flow for the soup in liters per second. But now what the 3 is talking about, well, we'll just say the 5 is the same as above. Talking about that answer. But the 3 is the number of liters of soup in the vat at the start. So what that means is you've got your 3 right here at the beginning, and on this orange one, oh, I just realized I flipped my colors here. Sorry, this 14 should be green and this 15 should be orange. Oh well. So for this one, the 3, it actually started with 3 liters of soup in the vat already. So then it started coming out of the soup faucet at the same rate as the X-ray soup, but the flying soup, there were 3 liters of soup in the vat already when it started. So if we drew a little picture, there was already this much in there when it started. Then it started flowing in after that. All right, so we got 2 more soups to explore on our last page here. So complete the tables for vats 4 and 5. So we'll switch up our colors a little bit. We've got vat 4, which is V equals 2t plus 10. And we've got vat 5, which is 3t plus 10. So we're going to fill out our tables, we're going to put our numbers into our equation here, just like we did before. So we have 2t plus 10. And we're going to do the same strategy as what we've been doing the rest of this lesson, is we're going to find the relationship between the equation and the table. We're going to fill it out by using the equation, and then we're going to plot that into the graph when we're done. So our first t is 0. So V equals 2 times 0 plus 10, which is 2 times 0 is 0. If we add 10, we get V equals 10. Our next one, V equals 2t plus 10. We're still using that same equation. This time we're going to put in the next number. So now instead of 0, our t is 1. V equals 2 times 1 plus 10. And 2 plus 10 is 12. Okay, and let's do one more. We have V equals 2t plus 10. So this time our t is going to be 2. So 2 times 2 plus 10. First it was 2 times 0, then 2 times 1. Now it's 2 times 2. We're just going down the chart here. And we get 4 plus 10, which is 14. All right, well, I'm definitely seeing the pattern here. 10, 12, 14, 16, 18, 20, 22. All right, and if you weren't confident about those numbers, you could fill in your equation for each one. I'm just going to spot check my last one. If my t was 6, I would have 2 times 6, which is 12, plus 10 more. 12 plus 10 is 22. So I know we did it right. Okay, let's do our next one. We have V equals 3t plus 10. So if my t is 0, 3 times 0 instead of 3 times t. And we end up with a 0 plus 10. So V equals 10 for our first one. All right, so they ended up starting with the same volume in them. Let's see if it continues. So V equals 3t plus 10. I started out with that same equation. This time I am making my t 1. Last time it was 0. This time my t is going to be 1. So 3 times 1 plus 10. So 3 times 1 is 3, add 10 more, and we end up with V equals 13. All right, let's do another. So V equals 3t plus 10. So 3 times t this time is 2 plus 10. And we get 6 plus 10, which is 16. All right, so to me, this looks like we started at 10, but we're adding 3 each time. So I'm going to fill in that pattern. 10 plus 3 is 13, plus 3 is 16, plus 3 is 19, plus 3 is 22, then 25, and then 28. So if I want to spot check and see if I did it right, I'm going to plug in my 6 for my equation. 3 times 6 is 18, plus 10 more is 28. So I know I did it right. So time to graph, which is number 17. Plot the points for VAT4, which is 2t plus 10. So we have 0, 10 for our first coordinate, 1, 12, 2, 14, 3, 16, 4, 18, 5, 20, and 6, 22. Does it make sense to connect those? Yes, for the same reason as before. The soup is coming out in between seconds, so we need to record the volume in between those seconds as well. All right, let's plot our second set of data here for VAT5. Oh, we forgot to say what kind of soup this is. We've got VAT4 is lightning speed. That's our pink one. So this is the super fast one, lightning speed. And then VAT5 is invisibility. All right, and I'm not sure, I wasn't looking at the screen on my video. I might have done all this work over here and you might not have been able to see it. I just realized I was looking at the book and it might have been off the screen that whole time. If it was, I apologize. Pay more attention to that in future videos. Okay, so if we go ahead and plot this information, we have 0, 10. Oh, they have the same first coordinate. 1, 13, 2, 16, 3, 19, 4, 22, 5, 25, and 6, 28. So we'll get those connected. And then we can answer the last set of questions. So tell whether the soup is flowing into the vat at a constant rate. So if it's a constant rate, it will have the same unit triangle. So this, for the pink one, the speed soup, over 1 up 2, over 1 up 2, over 1 up 2. Yes, this is definitely a constant rate because all of those unit triangles are the same size. For our green one, our invisibility soup, it's over 1 up 3, over 1 up 3, over 1 up 3, over 1 up 3. Yes, it's always over 1 up 3. So yes, it is a constant rate. I got kind of sloppy there, but yeah, it's always over 1 up 3. So they are not the same rate as each other. The unit rate for our pink speed soup has 2 liters per second, but the unit rate for the invisibility, the green one, has 3 liters per second. So they do not have the same unit rate, but they do move on their own at a constant rate because the unit rate for all the pinks is the same and the unit rate for all the green triangles is the same. All right, so we're almost done. What do the 2 in this equation, so they want to know about the 2, and the 3 in the next equation tell you. So it's asking, what are the 2 and what are the 3 telling you? It's the rate for both of these. It's the rate of flow for the soup. in liters per second. So on the pink speed one, it's coming into that vat at 2 liters per second, and the green one is coming in at 3 liters per second. So the green one is actually filling up faster, which you can see in the graph too, that the numbers are higher. You can see that it has a steeper slope, and so it's actually filling up that vat a lot more quickly than it is in the pink one. The pink one's shooting out more slowly. Okay, so our last question, what does the 10 tell us in 2t plus 10? And what does the 10 tell us in 3t plus 10? So the 10 tells us that for both of these, there was 10 liters of soup in the vat at the start, which is what our graph shows too. If the graph would have started down here at 0, 0, that would be showing that there was nothing in the vat when it started. It was empty, but that wasn't the case. For whatever reason, the speed soup and the invisibility soup, there was already 10 liters of soup in those vats before it started flowing in. Well, that wraps up our lesson for today. I know that was quite lengthy. My camera here is coming up on 37 minutes, but that's similar to what class is like. So what I will do is I will get a copy of the homework online, and I will post that. It's something that you can print or you can fill out digitally if you have a way to do that. If not, grab a piece of notebook paper and you can just put, hey, for number 1, here's my answer. For number 2, here was my answer. That might get a little bit tricky on the graph one, but give it your best shot. So we're going to do the best we can with the materials we have, and remember, this work is suggested at this point, so if you are able to keep up, we're going to offer dojo points for anything that you guys get done. So if you send me a copy of your homework that you already completed, you'll get your dojo point, and we'll figure out some cool rewards that you guys can spend those dojo points on. So send me that either on Teams or email it to me through your Outlook on your My Apps, or your parents can send me a picture on Dojo of what work you've been doing for this homework. Again, this is lesson 5-12. And for morning class, yes, you guys already did this homework because we've already done this lesson together. This is the last one we did together. But all that homework is at school. I don't have it. And it's been almost a month since you did it anyway. So I think it'd be worth your time to refresh your brain, make sure you know how to do it. And then afternoon class, you guys haven't done this yet. So good to see you guys on Zoom. Hope you guys can log in for our next session, and we'll talk to you later.